We got some experience using our definition to find derivatives of specific functions. It turns out that if we were to, we're able to generalize the derivative for different kinds of functions. For example, a polynomial function is a very easy function to find a derivative of. In general, we have a rule that says the derivative of any power, x to some power, is going to be, just bring that power down out front and subtract 1 from the exponent. All right, so for example, if we had the function f of x equals x to the 10th, or f of x equals x to the 9th, or h of x equals x to the 10th plus x to the 9th, and we wanted to find their derivative. One thing that we could do is look these up in something like a table of derivatives. This is an example from the OpenStax text. We have our formulas, and then we would just use these formulas based on the function, whatever f is. Maybe we have a second function g, so on and so on. But here I'm just going to use the symbolic computing library of Python, SymPy, define our functions, and then we can find the derivative using the computer. So instead of x being a domain of values here, x is just a symbol. And I can take the derivative of f with this diff function, taking the derivative of f of x with respect to x. Plug that symbol in, take the derivative with respect to that symbol, and sure enough, we get what follows from that rule, right? The derivative of x to the 10th is 10x to the 9th. We'll bring that power down, bring 10 down, subtract 1. Derivative of x to the 9th turns out to be 9x to the 8th, and the derivative of x to the 10th plus x to the 9th is just the derivative of f plus the derivative of g, right? It's just the derivative of each of them added together. And this also is a general rule for our derivatives. In other words, the derivative of a sum is the sum of the derivatives. And then it just depends on what kind of other, we can have some other functions. For example, trigonometric functions, sines and cosines. Here, if I'm using a sine, a cosine, or any non-integer kind of number, like the sine of something, or cosine of something, exponent of something, log of something, and I'm doing symbolic work, I need to use SymPy instead of NumPy. I won't be able to find a symbolic derivative if I try to use NumPy to determine this function for the sine or cosine here. But the derivative of sine is cosine, derivative of cosine is negative sine, and again, that sum rule holds. Okay, the derivative of the sum of those two functions is just the sum of their individual derivatives. Last kind of functions we're interested in for now are going to be exponential and logarithmic functions. So this is our natural log, this is e to the x, the sum of them, and then actually instead of just e to the x, more generally any base a to the power x as an exponential function. The derivative of the logarithm, natural logarithm of x, is 1 over x. The derivative of e to the x is just e to the x. Of the logarithm plus e to the x is just the sum of them again. And more generally, any base to some power, its derivative will be that same base to that power times the logarithm of a. All right, and then we can combine these into as complex expressions and functions as we would like, and use these basic rules to determine those derivatives. The real powerful one is this, that the derivative operation is a linear operation. So, very handy.